our mini-series on conics. Today we are talking about the ellipse. Now if you watched the video on the parabola already, you'll recall that the parabola was defined as the set of all points are equidistant to a point and a line. We called the point the focus, and we called the line the directrix. Foci is actually just a plural of the ellipse. If you haven't seen the parabola one yet, you can go back and take a look at that one, but we're going to build it off of that definition. So instead of the foci, the focus, the singular, we're going to be using foci, which is actually the plural of focus. All right. Now, the way I like to think of this is the ellipse is just an expanded circle. So if I take some kind of circle, in fact, a lot of classifications even consider a circle to be ellipse, and a circle is a special case of an ellipse where I have equidistant everywhere. The ellipse is kind of expanded, so back when they were first looking at these in the 1600s, they had two different classifications of it, the circle and the ellipse, and then they started to consider them one, and that kind of changed back to consider it two distinct. I like to look at it as two distinct, but we can look at a circle as a special ellipse where I have equal distance to all sides. So the circle had some distance here r and some distance here r. Now imagine what's going to happen if I grab this circle here and here and I pull this way and I expand that circle. Well, isn't this side going to get longer if I pull that apart? And my top side is going to collapse. So if I look at this, I would have a center still, but I couldn't say that it's going to be an equal distance from my center to any point, because if I grab this point, well, that's a relatively short distance. And if I grab this point, well, that's going to be a longer distance. So that definition no longer holds for an ellipse if I grabbed and expanded my circle. But what's going to happen is this, think of this center splitting. So I still have the center, it's right there, but I'm going to get these two new points, which are called my foci. Foci is the plural of focus. So my foci are now going to be here and here. And now if I look at this, if I grab a point here, the distance from here to here, that's sum. Let's call this C1. Let's call this C2. So C1 plus C2 is going to be some constant. That's going to be some distance. Now, if I grab another point, let's say an arbitrary point over here, the distance from here to C1 and here to C2, let's call this D1, and let's call this D2. So C1 plus C2 is going to be equal to D1 plus D2. I'm going to have the equal sum, and that's the definition of an ellipse. And this can be true anywhere. So these points that I picked are arbitrary points. I can pick a point here, and I'm going to have the same sum there. If I call that E1 and E2, this would then be equal to E1 plus E2. If I looked at another one, let's say here, that's going to be the same thing, and I can call those F1 and F2. So it would be plus F1 plus F2. So that distance of that line. Now, notice what's happening. If I take a said line, and let me go up here so I don't get too cluttered. If I take this ellipse like this, and I say that this is my foci and this is my foci, and I take an arbitrary point, let's say this red point here. Well, notice that this distance is a relatively short distance, but this distance is a longer distance. Now, if I move this point along this way, well, what's going to happen? This distance is going to increase. So the distance from this point to that point is shorter, but the distance from here has increased. But the distance from here has decreased to compensate. So they're going to increase and decrease very proportionately. And then if I'm over here, well, they basically split spots. This is now short, that one's going to be long. So that's going to be an equal sum everywhere. And even if I go over here, now my ellipse is not drawn to scale, so that looks like it's longer. But if I had my ellipse to scale, and I had my foci in the right spots, that's going to be equal distance everywhere. And we're going to look at that right now. So that's my definition. Now I'm going to clear the whole screen, so if you want to get that definition down, go ahead and pause the video and get that definition down. But to get more room, I'm going to wipe it out. Alright. So we're going to look at some definitions of the ellipse and just look at what's going on here in the picture. So if I have my general ellipse, I'm going to center him at the origin. So if I put him here at my origin, we're going to have some point here, which is a foci, and some point here, which is a foci. So generally we're going to call this foci 1, and we're going to call this foci 2. So foci is the plural of focus. Now, we're going to define the distance from the center. Right here is my center, and this is HK, which at this particular point is 0, 0, but the center is just going to be HK. Now, we're going to find the distance from the center to the major vertex, which is going to be this distance here. And sorry, the picture is going to get a little bit cluttered. It's going to be this distance here is going to be A. So we say A is the distance from the center to the major vertex. Now the major vertex is going to be the 2 points from, and this is also A. And it's positive because the distance is going to be a positive value. The major vertex is going to be on the major axis. So I have two different types of ellipses. I have this ellipse where this is my major axis. And this would be my minor axis up here. Or I can have the ellipse this way. And in this case, this is my major axis. And this would be my minor axis. So it's the A is the distance from the center to the major vertex. And we're going to say B is the distance from the center. This is your minor vertex. So B is the distance from the center to your minor vertex. And down here, this would also be a distance of B. And the distance from the center to the foci is C. All right, it's a little bit cluttered in there, but we've got this is A, this is B. So A is from the center to the major vertex, B is from the center to the minor vertex, and C is from the center to the foci. Now, if I turn this picture around, the definitions still hold. So if I let this go this way, very similar thing. This is going to be my center, which is HK. This is going to be B, and I'll put it in green again. So B is going to be the distance from your center to the minor vertex, and here B this way is your minor. A is going to be to the major, so this distance here is going to be A and A, and in here you're going to have your foci. Now your foci are always going to fall on your major axis, so that distance would be C, and this distance would be C. So your foci will always be at the major axis. Now the major axis could be the x-axis, or the y-axis is just the longer of the two axes. So there's some definitions. Now if I look at the point here, to be an ellipse, the distance from any given point to the foci, so if I take, say, let's go over here, let's take this point, and let's say that this is my foci and this is my foci. Well, the distance from here to here, that sum, is going to be the same as if I take this point here from there to there. So that distance is always going to be the same. So let's calculate what that distance is, and we're going to use, let me clear this again, and let's get a clean picture. So here is my ellipse, here is my center, right here is the foci, the major vertex, and the two foci. Now, if this distance here is C, and this distance here is C, well, we are centering it right now on the origin, but it doesn't really matter. I can be anywhere. But if I center it on the origin, then this point here is going to be the point C0 because I'm on the x-axis. Now, if this distance here is A, then this point is going to be A0. And likewise, if I go backwards C, this point is going to be the point negative C0. And this point over here is going to be the point negative A0. And likewise, we'll deal with these more in the next video, but this one is going to turn out to be 0b because the y-axis is moving, and this one is going to be 0, negative b. Now, if I want to look at the distance from each of these foci to that a value, because notice that this a value here falls on my ellipse. In fact, let's make it blue. This falls on my ellipse, so that's got to satisfy the equation. So the distance from this guy right here to here, let's figure out what that is. Well, from here to here is going to be C. From here to here, that's going to be A. So that distance is going to be C plus A. Then it's going to be plus, so that's going to be the distance from foci 1 to the major over C. And then we're going to have this point from here to here. Now, all the way across, that's going to be A, but I have less C. So that this distance is actually going to be my A value minus my C value. So it's then going to be plus A minus C. So I have C plus A minus C. Well, combining like terms, I get 2A. These C's actually cancel out. So my distance everywhere is going to be the length of the major axis, because that makes sense because the distance across the ellipse. So anywhere that I have is going to have a distance of 2A. All right, let's go ahead and end this video there. But we're going to pick up with that next time. And remember, the distance from any point, so if I take this point here, the distance from here to this foci plus the distance from here to this foci has got to be the same as 2A, because the ellipse has got to be done everywhere.